Hi, we are going to talk about heat energy and temperature change. This is going to be the most frequently used formula or equation that we'll use in Form 3, okay? Q equals mc delta T, okay? First of all, let's have a look at this question. I have a glass of cold drink and I want to make it hot. How much energy is needed? We have already learned about power. It means in a certain period of time how much energy is being given out if the heating up is quick or it is slow. But the amount of energy needed we have not talked about yet, but this is going to be covered today. And in order to answer this question, it doesn't make much sense how to calculate or things. There is not even a number because the question is not specific enough. A glass of water, how many are there, and how make it hot, how hot. So we'll address the problems one by one, and at the end we are going to derive the equation which determines how much energy actually is needed. Okay, the first problem is a glass. A glass is so big, it can be a big cup, it can be a small cup. Okay, of course a large cup of water will need more energy to heat up, and a small cup of water would need less energy to heat up. So the relationship here is that we have to specify what is the exact amount. But let's say if you are measuring liquid, it can be in ml, it can be in L, liter, or it can be in kilogram. And in science, we always standardize the units to be kg. This is called the SI unit in kg. Okay, so in order to specify the amount, we use kg. And the relationship here, large cup need more energy, small cup need less energy. The actual relationship is in this proportional. Okay, what do we mean by proportional? It means more and more mass will require more energy. But not only that, double the mass will need double the energy. For example, 1 kilogram of water, if you need 1000 joule for 1 kilogram, then you can tell for certain you need 3000 joule, 3 times for 3 kilogram. Okay, this is what we mean by proportional, 正比例. If you are double, I am also going to be double. Okay, here we are going to have an experiment to show this relationship. Let's say in 1 cup of water there is less, only 0.2 kilogram. This cup of water there is more, 0.3 kilogram. And then how do we derive the relationship between the amount of water and the energy needed? So we'll use joule meter to measure the amount of energy we need to increase the water temperature by 10 degrees Celsius. Okay, and then we plot it into a graph. So here in 0.2 kilogram of mass, it will need less energy. For example, it is like 8 kilojoule. Okay, and for the 0.3 kilogram of water, and that means more water. Okay, here the x-axis is measuring the mass. So more water will need more energy. Here it is 12 kilojoule. So 8 and 12, the ratio is 2 to 3. And also this straight line pass through 0. So by the knowledge of proportional, 正比例, you know that if you are 2 times, then I am also 2 times. Okay, the relationship between the heat energy needed and the total mass is in proportion. This is the first point. And for the question, we can modify it to be more clear. I have not just a glass of drink, it should be 0.2 kilogram. Okay, be more specific. Okay, the next problem is make it hot is also vague. Okay, how hot? For example, if the cold water is 10 degrees Celsius and the hot water is 90 degrees Celsius, this is a 80-degree increase. Okay, this is the change in temperature. The change is 80 degrees Celsius. But for the second case, for example, the cold water is 25 room temperature to 65. This is quite hot in a bath, okay? But this amount of increase is just half of the previous. It's just 40 degrees Celsius increase. Then the energy needed will also be half, because when we have the exact amount of temperature change specified, and making use of these second properties, the heat energy needed is proportional to the amount of change in temperature. So for 40 degrees Celsius, the amount of energy needed is half of that of 80-degree change. Okay, we will also perform an experiment to show this relationship, the relationship between the heat energy and the change in temperature. So in this experiment, we have a cup of water. So we choose 0.2 kilogram. You can choose other, but that is what this textbook one use. Okay, and then this curly bit is the heater. Then we use the joulemeter to measure the amount of energy given to the water to heat it up. Okay, and this thermometer, of course, is measure the temperature of this water, and we have to stir it, 攪勻佢, so that the water temperature is evenly distributed. Okay, and this graph, this is a different graph. Okay, it may look similar because the energy, the y-axis measure the energy needed, but the x-axis is no longer mass this time. This time is measuring the change in temperature. For example, if the water temperature rise by 10 degrees Celsius, then we can look up how much energy is used. Okay, between 6 and 12, this is 9 kilojoule. Okay, indeed, I have already drawn it out. Okay, if we want the water temperature to increase by 10 degrees Celsius, we will need to provide 9 kilojoule of energy to the water so that the water will heat up by 10 degrees Celsius. Okay, and if we want to further increase the temperature, for example, to 20 degrees Celsius, then according to the graph, it is exactly double of 9. It is 18 kilojoule of energy is needed to provide to the water so that the temperature will increase by not 10 but 20 degrees Celsius. Okay, so this is the second relationship we have observed, is the heat energy needed is proportional to the change in temperature. More change in temperature, more heat energy is needed. Not only the same direction, the amount is exactly proportional. If you are double, I am also double. Okay, so here not only make it hot, but we can specify, for example, heat up by exactly 50 degrees Celsius, then how much energy is needed. So can we calculate it already? No. Actually, there is a third properties that we have to know. Apart from the amount, which is the mass in kilogram, and the change in temperature, how much degrees Celsius it is increased, the third thing we have to take care of is the type of material. Okay, actually Q 等於 mc delta T. This is the outcome we are going after. And apart from the mass m and the change in temperature delta T, we can see a small letter c here, which is related to the type of material being heated up. For example, if the drink is water, then it will be very, very, very difficult to heat up because water need a lot of energy to just increase by 1 degree Celsius. Milk is quite similar to water, but it is not as difficult because you can see here the number. If I have to heat up the water, I need 4,200 joule of energy per kilogram per degree Celsius. But for milk, it is less, just 3,890 joule of energy per kilogram per degree Celsius. So every type of material, gold, glass, iron, they will have a specific measurement, a specific number, which we call specific heat capacity. So each material have a number. For example, here in the textbook page, I forgot 31 or 36, you can see water is say 200, and glass is 600, gold is just 129. So there are different numbers for different materials. Okay, we'll see what is the properties, what we derive, but let's make use of what we have learned for now. So apart from just drink, we have to say what type of drink it is. So let's use water, and then we want to calculate the energy. The formula is like this: the energy is equals to mc delta T. Delta T, yes, okay. So mass, material, specific heat capacity, it is, and change in temperature. This is Q 等於 mc delta T, okay. This equation, memorize it. You will use it all the time. Now we calculate how much energy it is needed. So Q 等於 mc delta T, Q is equals to mc delta T. Mass is 0.2 kilogram, always convert to kilogram. And water, we can check the table. The C is 4200, okay? This is for water, 0.2 kilogram water. And then what is the change in temperature? Delta T, it means change in temperature. If this is from 10 degrees to 30 degrees, then it will be 20 degrees difference, okay? And here it says 30 degrees Celsius increase. So we plug in these three numbers to the calculator, and then 0.2 times 4200 times 30, and then you can get this number, 25200 joule. Okay, that is how we calculate the energy. Okay, so we learn one more thing. Okay, we know Q 等於 mc delta T. Okay, this is what we know. But what about if Q is not what we are after? If Q is provided, let's say 50,000 joule of energy is provided, and we want to know what is the change in temperature in this case. Okay, now we are more experienced, so we know material need to be specified. Let's say water. Okay, so water is say 200, and the mass is needed also 1 kilogram. So make use of the equation. Q is 50,000 joule, mass is 1 kilogram. Okay, mc delta T. C is water, and look up from the table, water is 4200, okay? And then delta T is what we want to calculate, and then rearrange it into mixing subject of delta T. It will be 50,000 divided by that, which equals to 12 degrees Celsius. That is the answer. So if 50,000 joule of energy is provided to water, it will increase by 12 degrees Celsius. So if you have room temperature, let's say 20, it will just rise up and become 32. That is a huge amount of energy, but just give rise to 12 degrees Celsius of change actually. Now, practice one more time. If we don't use water, if we use iron, how do you think the result will change? So from this table, we have to look up iron. The specific heat capacity of iron is 480. So we plug it in. Q 等於 mc delta T. Okay, so rearrange that. You have the same format, but this part, the denominator, 分母, is smaller. So the change in temperature will be, the denominator is smaller, so the change will be larger. Okay, 除一個細啲嘅數會攞到一個大啲嘅數值。Okay, so it's no longer just 12 degrees, it will be 104 degrees Celsius. You have to know the same amount of energy. We just change the material type. Because the specific heat capacity is much smaller, the change in temperature is therefore much larger. Okay, so let's go to the end. For example, gold. In this table, gold have a smallest specific heat capacity, C. Okay, so when we change it to gold, the number is changed to 129. And then the same method, the change in temperature is almost 400 degrees Celsius. If you touch it, your hand will get injured. Okay, so have a look here. The same amount of energy is given to these three types of materials, but the specific heat capacity is different. For gold, it is small. For water, it is very large. And the result is the change in temperature will be very, very different, because the specific heat capacity is indeed how difficult it is to heat it up. Okay, you can forget some of the material we have covered, but you have to take this away. The size of the specific heat capacity is an indicator of how difficult it is to heat something up. And water is very, very, very difficult to heat up. If you have a look at the textbook first picture here, you can see noodles and noodles. This is tong mian, this is chao mian. Anytime you order something with water or soup in it, it will last much longer until it gets cold. Have you ever experienced that? That is because the specific heat capacity of water or soap is much larger, so it can be it will cool down much more difficultly. It is more stable in this temperature. Okay, so the takeaway is that large specific heat capacity means more difficult to heat up. Small specific heat capacity means easier to heat up. Okay. Summary. All you have to remember is pack into this small package of Q 等於 mc delta T. But what does it mean? Q is the heat energy needed to heat something up. Okay, and M means mass. The more material you have, the more energy you needed. Okay, very trivial. And so, and also, delta T means the change in temperature. If you want to have a small increase, you need little energy. If you have a large increase, you need more energy. So, these two proportional relationship is here, M and delta T. But the third thing is C. The name of C is specific heat capacity, and it is only depending on the type of material, and water is having a large one, so it is very difficult to heat up water. Okay, so that is all for this part. Thank you for your attention. Bye bye.